Hey guys, this is Rick from MathX, and today we're going to be doing the number 9 and 10 from the F is equal to MA exam A of 2020. Now, these set of two problems are actually pretty easy. However, they look a bit intimidating at first glance. So in this video, I'll just be going over these problems and an easy and comprehensible way to solve them. So without further ado, let's get into it. A block of mass m is attached to a massless string. The string is passed over a massless pulley, and the end of the string is fixed in place. The horizontal part of the string has a length L. Now a small mass m is hung from the horizontal part of the string, and the system comes to equilibrium. Neglecting friction everywhere, the tension at the end of the string is So, the setup for this problem is quite simple. We have a string that's fixed to a wall, and it's holding a mass. And then another mass is hung on the horizontal part of the string, pulling the mass that already was on the string a bit upwards. And now the question is asking for us to find the tension at the end of the string. So when it means end, it means where this small mass is located. So, just like every force problem, we should draw a free body diagram for all the forces that are acting upon this mass at the end of the string. So here's the point to represent the center of mass for this mass. Here's the downward force of gravity acting on this mass. And here's the upward force of tension. Now, since it says that the system comes to equilibrium, we know that this mass has no net acceleration, which means that the sum of the forces must be equal to 0. So since these two forces are in opposite directions, we can subtract one another and set them equal to 0, since the system is at equilibrium. From here, we can just move over the gravitational force to the other side, and we get tension is equal to Fg, where Fg is the force of gravity. That means tension is just simply mg, because Fg, the force of gravity of any object, is just its mass times the gravitational acceleration. So here we see that T equals mg, giving us the first answer to the first part of the question. Notice that this additional mass didn't change the tension whatsoever, showing that all this extra stuff was just clutter. If you just draw a simple free body diagram and think about what's really going on, this first part of the question can be solved quite easily. The second part is a little more tricky. During this process, the block has been raised by approximately a height. So basically, now we've already found the tension in the rope. But now, after adding the second mass, we need to find out how much this initial block has been displaced. We need to find this length shown in the arrow here. So this will require a bit more thinking. But once again, we can think about this using our free body diagrams. So since we're trying to find out the height has been displaced, there's one thing we need to keep in mind. Since we're dealing with the massless string, and we can assume that the string is inelastic and it cannot be stretched, pretty much whatever addition of string here, that is equal to the subtraction of string here. So if you figure out how much string is added from this diagram to this diagram in the horizontal region of this mass pulley system, we can figure out how much string was taken away from the vertical part of the mass pulley system. So pretty much what we need to do is we need to compute for the length of string in this diagram and subtract it from the length of string in this diagram. So we know that the length of string in the initial diagram is just L, because it just tells us that in the problem. But this might be a little harder to compute. However, we can get an idea of the length of string in this diagram if we draw the free body diagram for this mass. So here's the point to represent the center of mass of this mass attached to the center of the rope, the horizontal part of the rope. And here are the forces of tension acting on it. They each go in the upright and upper left direction. So these both represent the tension forces. And since it's a massless string, we know that these two tensions have to be the same. Along with that, there's also the force of gravity pulling the string down. So here is the free body system for this first mass. Since it says the system has come to equilibrium, we know that this mass also has to have a net acceleration of 0, meaning that the horizontal forces and the vertical forces cancel out. So it's pretty clear to see that both tension forces occur at about the same angle from the gravitational force. And intuitively that makes sense, because displacing it just kind of pulls both sides. It like pulls it down with respect to both sides. So we know that the horizontal forces have been canceled. However, we see that the vertical forces have not been canceled. In the upwards direction, we see that the tension forces are acting, and in the downward direction, we see that the gravitational forces are acting. So in order to set the vertical forces equal to 0, we should define an angle here, theta, and then say that Fg has to be equal to the vertical component of each of these tension forces. So this tension force has a vertical component of t sine theta, and this tension force has a vertical component of t sine theta as well. So the net vertical force that they exert is 2 t sine theta. And as I've already said, the cos theta forces for these tensions cancel each other out, so we don't even need to worry about the horizontal direction. Now that we have this equation, we can start substituting back in values, like m's and g's. So we know that gravitational force for this mass is the same as the gravitational force for this mass, so you can substitute it with mg as well. And then from our first question, we know that the tension force, which is uniform throughout the entire string because the string is massless, is also mg. So we can write, instead of 2t, we can write 2mg. And then we put the sine theta here. From here, we can pretty easily cancel out mg from both sides, giving us 1 is equal to 2 sine theta, or 1/2 is equal to sine theta. Taking the sine inverse of both sides, we get that theta is equal to 30 degrees. So then we know that this angle theta from this incline that I drew with respect to gravity force is 30 degrees. So if I draw it on the original thing, just for a better understanding, we know that this angle is 30 degrees. And then, since this plane I drew is parallel to the ceiling, we also know that this line is 30 degrees. So pretty much using this information, we can find the length of this string. So we could either do it in one of two ways. We could either just take account for the fact that this is L by 2 and then just compute this using 30, 60, 90 triangles. However, I just like to use a nice trick that I've learned from doing math competitions. In this kind of situation, we can honestly just reflect this line segment over our imaginary plane here, and it gives us this line. Now we know that this part is L, so we know that cos 30 is equal to L by this mysterious length we need to find, x. I'm going to call it x. Which means that x is equal to L by cos 30. So this is the length of our string in our final diagram. L by cos 30. So now that we found the amount of string in the horizontal section in the final diagram, and we already knew the amount of string in the horizontal section in our initial diagram, we can subtract them to figure out how much string was added to the horizontal section. And as I said, once we do that, we figure out how much string was taken away from the vertical section. So we can do this by simply doing L by cos 30 minus L will give us our answer. So from here we can just factor out L, get 1 by cos 30 minus 1. And then once you compute for this value, you can just tag on to L and you're going to get your answer. So computing for the expression inside the parentheses, 1 by cos 30 minus 1, you should get about 0.15. And then multiplying that by L, because we had L here, would give us 0.15 L. So this is the amount of string added in our final horizontal section, which means that it's also the displacement in the final initial section, showing us that answer A is the solution to this problem. So here we just solved the number 9 and 10 from the F is equal to MA exam A of 2020. Now, this problem required a bit of work, but it was not impossible. And just by drawing simple free body diagrams and setting up some simple equations, we were able to solve for both questions, giving us an easy 2 points on this exam. So whenever dealing with these kinds of tension and force kinds of problems, always remember to draw free body diagrams. And if you're ever in doubt on what to do, just set up some equations, because both of these should be enough to solve most such force problems.